here's a symbol that was introduced in the previous lecture, the inclusion symbol. So the syntax is like this, and the way to read this in English is A is a subset of B. But how does the formalism work? So what are the rules? It's definition 6 for us. So this is the definition of inclusion. And it says A is a subset of B if and only if the following proposition holds. For all Z, if Z is an element of A, then Z is an element of B. So that's it. That's the definition. So you can think of A as a subset of B as this, and here the Z is bound by this quantifier. So there should be a way to read this or interpret this without mentioning Z. The Z is not really there. So how would you read this? All elements of A are elements of B, or every element of A is an element of B. That's what it means to say A is a subset of B. Every element of A is an element of B. Now, why am I calling this a definition and not an axiom? I mean, what does definition even mean? So, in terms of deduction, you can treat definition basically as the same thing as an axiom. It's something that you can use as a starting point. It's a proposition that we just accept at the beginning as part of the initial setup of the deductive game that we're going to play. So definition is just like an axiom as far as deduction is concerned. So why is it called something different? Why don't I call this axiom 6? Well, remember last time I kind of ranted about how we really would like to have as few axioms as possible. I'm going to call certain things definitions to point out that they don't matter for the sake of that earlier rant. There's nothing, so it's bad to have lots of axioms, but there's nothing wrong with having lots and lots of definitions. Here's why. If we were to not make this definition, if we were to not include definition 6 in our system, then we would find ourselves writing things like this a lot, and we would just have no way of writing them in this nice, shorter, more compact way. And it would be annoying, right? But that's it. That's the only change. That's the only thing that would change if we left out this definition from our system. The only thing that would change is that we would be annoyed every time we write this because we don't have a shorter, more compact way of writing it. Including definition 6 or leaving it out does not change how many things we can prove are true. It does not change which propositions we can prove are true. I mean, technically it does because we can never use this symbol. But if you think about what a proposition is saying rather than the way the proposition is said, including definitions does not change. Including or excluding a definition does not change does not change which propositions you can actually prove. So you can make definitions all day. Invent a new symbol, give it a definition, and there's no harm there. There's no chance of proving a contradiction coming from a definition. So the reason it operates like this is because with a definition, if the symbol being defined creates a proposition, like the inclusion symbol here, then the definition is just going to have something involving that symbol, and then a double arrow, and then something not involving that symbol, using only symbols that were introduced previously. Another kind of definition that you will often see is one where instead of a proposition, instead of a symbol that creates a proposition being defined, you would see a symbol that creates a term being defined, and then you would see an equal sign. But that is the idea. So let's go into semantics mode for a second and just think about the intended meaning of definition 6. Here's how I think about it. So I imagine a set to be a collection of things, a disordered pile of things, kind of just maybe a bag of items. And let's say I have one bag of items, A, and another bag of items, B. And inside the bag, I've got some stuff. So maybe I've got something called X, something called Y, something called P. When stuff is inside the bag, I use the membership symbol to describe what I'm imagining in that situation. So here I would say X is an element of A, or X is in A. Y is in A. P is in A. But I would not use the subset symbol. That would not apply here. So I would not say X is a subset of A. To say that one thing is a subset of another thing is to say that all the elements of the first thing are also elements of the second thing. So let me draw a situation where A is a subset of B. P, and then let me also introduce Q and W. So here's a situation where A is a subset of B. Every element of A is an element of B. Now, it could also be that A itself is an element of B, but that's unrelated to whether or not A is a subset of B. So in this situation, I would say that what I have on the left here is a subset of what I have on the right. So you see the difference between subset and element? When you think about element, like this symbol, think about, oh, when I open this box, I see this item inside. And when you think about the subset, this symbol, imagine that you have two boxes, A and B here, and if you were to open the left box and pick out any item, then you would be sure to find a copy of that item in the right box. So these are very different, and they're often confused by beginning Math 8 students. Membership versus inclusion. And here's something that doesn't help. It doesn't help that the language used for these two is often really, really similar. So here's a way of saying this in English. You can say it like that. Here's a way of saying this one in English. Wow, those are very confusingly similar. I've also heard this. Sometimes I say this. A is inside B to say A is a subset of B. They're really similar, but they stand for very different ideas. If you really want to make the distinction, then you can use more clear language like this. A is an element of B, or A is a member of B. And here you can say A is a subset of B. So I very much advocate preferring these ways of talking and this way of talking until you're very used to these ideas.